Hello everyone, welcome to this week's Geophysics Department Seminar. I'm pleased to introduce our speaker for this afternoon, Josimar. A quick background on him. Josimar received an undergraduate degree in geophysics here from University of São Paulo and a PhD in geophysics from MIT. In his research, he investigates the physics of natural and induced earthquakes in the context of subsurface energy and environmental activities, such as wastewater injection and geological carbon sequestration. Currently, Josimar is a postdoctoral associate at Harvard University, where he's working on advancing the understanding of the impact of long-term oil and gas operations on induced seismicity in the Los Angeles Basin, California. Before we begin, let me remind you that there will be time for questions at the end of the presentation, so you may write your questions on the YouTube chat and I will read them to him. So thank you, Josimar, for accepting our invitation, and over to you.
Sounds good. So let me share my screen. Okay, can you see my presentation?
Yes.
Okay. So good afternoon, everyone. So thank you very much for the invitation to present a little bit of my work here in this seminar. So I'm Josimar Silva. I'm a former alumni from IAG USP, and then recently I received my PhD 2 years ago in MIT in geophysics, and since then I'm working as a postdoctoral associate at Harvard University. And the title of my work is Induced Seismicity Associated with Wastewater Injection and Geological Carbon Sequestration. And the ideas that I will give you, sorry. Can you see the presentation again?
Yes.
Okay, sorry, I just pressed something wrong here. So the ideas that I will give you a perspective from the coupled multiphase flow in geomechanics. So most of this work, or actually the entire and the whole work, was actually done during my PhD when I was in MIT. And I'll give a little bit of overview of what I'm doing now as a postdoc as well. Okay, so just to set the context, so what is happening here, at least in the United States, is that since in the last decade, we've been seeing a very sharp increase in the amount of induced seismicity associated with wastewater disposal. In fact, when you look at the number of earthquakes of magnitude larger than 3 over time, we can see that around 2010, there is a significant increase in this induced seismicity in the central United States. And we know that this induced seismicity is actually associated with wastewater injection, which is a process where the oil companies, they take water that comes from the hydraulic fracturing operations and then inject those in subsurface. And this is such a, it's been such a dramatic increase in the number of earthquakes that the USGS, or a group formed by the USGS people, they computed the chance of a likelihood of a minor to damaging earthquake in the central United States. And in 2018, you're as likely to suffer some damage from these earthquakes due to wastewater injection as if you were living in California. So of course, this has a little bit of is a problem for people who live in central United States, because as you know, Oklahoma, for example, is not in an active subduction zone, for example. So we understand relatively well the ways that we can initiate earthquakes in subsurface. So for example, in this sketch, we can see that there's 2 primary ways that we can actually move a persistent fault towards destabilization. In the first way, we can inject fluid in subsurface, and then we're going to pressurize a certain reservoir, and then that is in contact with a fault. And this direct pore pressure effect is going to lead to a reduction in the effective normal stress and move the fault towards destabilization. In a similar way, if you have a reservoir that is on top of a fault, sitting above a fault, and then you load this reservoir with some fluid changes, and then basically the idea is there is some volumetric stress changes that cause poroelastic stresses at the fault. So in this case, there is no direct pore pressure effect. It's just purely a poroelastic effect, meaning that you change the loading above the fault, for example. So these are the two primary mechanisms that we can induce earthquakes. There is others perhaps, but these ones are the main ones that we think are the most important ones in this case. And there is a number of cases where human activities can induce earthquakes. So for example, there is the case of wastewater injection that I mentioned before, but geothermal energy also is a case where you can actually induce earthquakes during this enhanced geothermal energy. And of course, there is the case of CO2 storage in geological formation, which is, I will explain a little bit in here. So the idea is that we want to dispose of carbon in geological formations, and that process also can induce earthquakes. And this process can range from simple single-phase flow systems where you have water injected into water, and then to more complex multi-phase flow systems where you have CO2 being injected in a brine formation. Okay, so I wanted to just set the stage of how do we bring a persistent fault plane closer to failure. And so if you start from a simple sketch where you have a fault plane, and then there is a reservoir that is in contact with this fault plane. So we know that this fault plane is subject to normal stress and shear stress. And according to the Rubert and Rubin effective stress law, the idea is that this fault will slide when the shear stress acting on the fault exceeds the shear strength of the fault, which is given by the friction coefficient times the normal stress minus the pore pressure. And we call this term the effective normal stress. So there is few ways that we can actually bring this fault close to failure. So for example, you can, if you plot the shear stress versus the effective normal stress, and then this is the failure line where the fault would slide. So the idea is that one way that you can bring this fault plane to failure is that you can actually increase the shear stress at the fault. Another way is that you can decrease the normal stress at the fault, which has a similar effect as increasing the pore pressure. So in both ways, you're reducing the effective normal stress at the fault. And another way, of course, you can do all this together. The shear stress and the effective normal stress are all changing at the same time, and then this variation leads to the fault being moved towards the failure criteria. And of course, there is details. I'm not saying anything here about details about the friction coefficient of whether this fault is going to slip aseismically or not. That will depend on the details of the frictional properties of the fault. So for this simple case, we may be tempted to say, well, it's not that hard to predict the impact of injection and production in subsurface. We can maybe do some we can perhaps imagine what would happen in this fault plane for a given scenario. And then, we don't really need to do a lot of modeling, perhaps in this case. But I'm tempted to say that, most of the time, the geology that we find in subsurface is quite complicated. And is not composed maybe of only one fault. There is multiple faults. Sometimes the injection is not very simple neither. Sometimes a very complex injection and production schedules with multiple wells, some hundreds of wells. So I'm giving an example here of the Wilmington oil field, which is located in Los Angeles in California. So this is a project that I've been working on now as a postdoc. And here the idea is that we want to understand what is the impact of this long-term oil and gas production on the stability of this fault system that sits below the Wilmington oil field. And for this case, we really need to develop models that account for all the faults and all the complex production and injection schedules for the many wells that are in this field. So that's what I will show in the next slide. So I will show the development of this model that's the coupled flow and geomechanics model that I've been using to study induced seismicity. And the key concept that goes in this model is the Biot's theory of pore elasticity. So the idea is that pore pressure changes in subsurface, they lead to mechanical deformation. And conversely, this mechanical deformation also leads to pore pressure changes. And to develop this model, so we can start with the PDE for the fluid mass balance for multiphase flow system, okay? And then we can combine this with the balance of linear momentum and the effective stress law, and we can arrive at a fluid mass balance equation for a multiphase flow poromechanics system. And the idea is that we're going to solve this using this scheme called fixed stress split scheme, where we're going to solve the flow problem first and fixing the rate of volumetric stress changes, followed by the solution of the mechanical problem where the pore pressures are prescribed. And then we're going to iterate over this until a certain convergence value, and then we move on to the next time step. So to give you a little bit of feeling of what the model can do, I will give a simple example. So imagine that you have a sphere, okay, that this sphere is has very low permeability in general, and that the flow is allowed to exit the sphere through this outer shell. So if you apply a compressive radial confined stress in this sphere, what's going to happen is that due to the low permeability values of the sphere, the pore pressure is going to rise to its undrained value, which is this blue dashed line. So this pore pressure over time. However, due to this pore elastic effect, at the center of the sphere, what's going to happen is that the pore pressure is going to continue to increase. And this is because as the fluid exits the sphere from the shell, then the sphere is going to compact, which is going to induce additional pore pressure changes until its pore pressure then equilibrates with the exterior boundary. So this illustrates this coupling between flow and mechanics, which is important because if you want to capture pressure variations in conjunction with mechanical variations subsurface, you have to have this two-way coupling between flow and mechanics. And that's the model that I'm using to study induced seismicity in this presentation. Okay, so I will show two case studies where I apply this coupled flow and geomechanics model to real induced seismicity cases. So basically, the first case is the Rangaly experiment on earthquake control that happened in 1970. So this case is a wastewater injection case. And the second case is a case of geological carbon sequestration, which I'll show later on. So in this case, the Rangaly experiment, so it happened in 1970. So this was a partnership between Chevron and the United States Geological Survey. So basically, there's an oil field located in Rangaly, in the state of Colorado. And what they did is that they drilled, or they took some few wells, 4 wells in this case, near a very well-known fault in this area. And they performed multiple cycles of water injection and withdrawal in this area. And they recorded the earthquakes that happened as a consequence of this water injection. I just want to point it out that I have published 2 papers in this work. So if you're interested, you can follow this reference here. So when you look at so in 1976, there was a publication that came out in Science where they provided, where they showed for the first time this qualitative correlation between the reservoir pore pressure increase and the number of earthquakes. So basically what they showed is that here is the y-axis is the number of earthquakes over time, and the black line is the reservoir pore pressure. As you can see, as the reservoir pore pressure increases, there is more earthquakes, and then as the pressure decreases, the earthquakes stop. And the reason that this work is so important for induced seismicity is because the first time that they showed actually that this reservoir pore pressure variations due to injection can induce earthquakes, and you can actually stop the earthquakes by reducing the pore pressure in the reservoir. Okay, so what is the contribution that I want to give with this work? So basically, this previous analysis done in 1976, was provided a qualitative explanation for the correlation between pore pressure increase and earthquakes. What I want to do is to revisit this work using a mechanistic quantitative explanation using coupled flow and geomechanics. Basically, I want to understand why and how did the earthquakes happen in this specific injection operation. So the first step, so as I mentioned, we need to build a very consistent, hopefully very accurate geological model of subsurface. So in this case, the Rangaly oil field is composed of an overburden, and then there is a reservoir, which is the Weber sandstone. And then this reservoir actually is where the production and the injection takes place. And then this reservoir sits on top of a basement. And if you look on a map view, you can see that the reservoir is an anticline, so it's very shallow in this area and very deep elsewhere. And the earthquakes are located in this area. That's the ones that were induced by the injection process. And there are 2 main faults in the field. So there is one vertically oriented strike-slip fault, and then a sub-horizontal thrust fault. And the earthquakes happen in two clusters. One that I call it upper cluster, not the one that is called lower cluster. And they are separated by the lower cluster, by the thrust fault. And the idea here is that this lower cluster of earthquakes, this is outside of the injection interval. So we want to understand why did these events happen outside of the injection interval, whereas these other events are located actually inside the injection interval. So the first step after building a geological model is to actually build a computational mesh that is going to adapt to all the faults and all the horizons in this model. And this mesh is going to actually serve as the basis that we use to run our simulations. So basically, the idea is that we have very small elements at the faults and they course away towards the boundaries, and we use implicit elements to represent the faults in this case. Okay, I wanted to mention out some field measurements that they obtained during the Rangaly experiment. So basically, what I'm showing here is the pressure in the y-axis over time. And this is the data that they reported and that came out from the field experiment. So there is one period of injection followed by the water withdrawal, and then another period of water injection. And these squares, they show the pressure for different well locations that are shown in this figure on the right here. And the bars are the number of events. So I wanted to pay attention to these two wells, the P69 and Emerald 45, which are located in this block of the fault. So you can see that these wells, the pressure in those areas, it respond quite nicely to the different periods of injection and withdrawal. But if you look at these other two wells, UP29 and 67, which is located in this other side of the field, you can see that the pressures in those wells actually are pretty much insensitive to what is happening on these other wells. So this was a very important piece of information for us, because when you look at the locations of these wells, you can see that they are separated laterally, or they are separated by the strike-slip fault, which runs in this area here. So what it means in practice is that these wells, UP29 and UP67, they are compartmentalized. They are hydraulically separated from these other two wells, P69 and Emerald 45 in this case here. So this information is important for us because we can account for that in a flow model. But at the same time, there is earthquakes outside of the field, outside of the reservoir interval. And this also has to be taken into consideration, which means that we need to think that whatever happened in these wells that were injected also affected areas outside of the reservoir interval. Okay, so how did we reconcile this information? So in the way that we thought about the hydraulic model for this area, so basically we think, if you go back to the field, normally you see that the faults are normally impermeable in its core. So basically there is a core that is very impermeable. And then normally this core is surrounded by a very permeable damage zone, which is shown here. So the idea is that this damage zone is very permeable because it contains lots of microfractures that serve actually to transmit pore pressure to very far distance. So the conceptual model that we have is that there is the injection wells in one side of the field that are separated by the strike-slip fault, and then hydraulically isolate these other two wells here in the field. But at the same time, since we have earthquakes outside of the injection interval, we are allowing pore pressure to diffuse from the injection well into these earthquakes outside of the reservoir interval. And when you look actually at the results of the coupled flow in geomechanics, we can see that that's actually a very important aspect. So when I'm showing here on this figure on the left, so this is pore pressure changes from the beginning of the simulations. So this is along the strike-slip fault where the earthquakes are happening. And you can see that the pore pressure changes near the injection wells, which is inside the injection interval. This is quite large. This is around 10 megapascal. So the injection process actually, severely destabilized the faults in this area. But at the same time, there is a very faint amount of a very small amount of pore pressure that actually diffuse to this region outside of the injection interval where the other earthquakes are happening. And this pore pressure actually this fusion actually happens along this fault damage zone which serves to communicate the injection in the reservoir interval to this region outside of the reservoir interval. And interestingly, if you look at the shear stress that is induced due to this coupling between flow and mechanics, we can see that the total shear stress is actually decreasing in this area where the earthquakes are happening. So this is counterintuitive because it tells us that if there was no pressure communication between the injection interval in this area outside of the reservoir interval, so the shear stress will actually be decreasing. So the fault is actually being moved towards stabilization in this area. So, and this is a consequence of this volumetric expansion of the reservoir. So as you inject, so this induces a left lateral shear stress at the fault. So the fault is actually in a right lateral stress regime. So we're actually reducing the total shear stress acting in this region where the earthquakes are happening. So this points out the importance of pore pressure as a mechanism to destabilize these faults, especially in the areas outside of the reservoir interval. And I want to mention now then, my premise or my assumption here is that the pore pressure diffusion along this damage zone is very important to destabilize the earthquakes outside of the reservoir. So then the question is, what is the impact of this fault permeability, of this damage zone permeability, on the destabilization that we obtain on these faults? So basically, what I'm showing here is DCFF. So DCFF is the changes in Coulomb failure function. The idea is that if you just take the difference in different CFF over time, and the idea is that if DCFF is positive, we have fault destabilization, and if DCFF is negative, we have fault stabilization. So this figure here shows just the DCFF over time, and then the different lines are just different fault permeability values. And here's the upper cluster, which is the one close to the injection wells. So as you can see, if you're close to the injection wells, it really doesn't matter which fault permeability you choose for this case, because the DCFF is always positive, because here the pore pressure changes are so large that it destabilizes the fault no matter what permeability values you choose for the fault. But when we look at the lower cluster of earthquakes, which is in this region outside of the reservoir interval, we can see that actually the choice of this fault zone permeability actually plays a big role in the amount of destabilization that you obtain. So for example, if the fault permeability zone is if the fault zone permeability equals 0, then the amount of destabilization that you obtain is pretty much near 0. So we need to have some degree of fault permeability that allows this pore pressure to communicate between the injection location and the region outside of the reservoir. So, okay, so now we can ask another question. So we want to understand as well in this project, what is the contribution that tectonic forces have compared to the anthropogenic activities? And we want to say whether which cluster was induced or triggered by the injection during the Rangaly experiment. So basically what we're doing here, we're trying to measure how much are we moving the fault from its initial state to a final state. Okay, so basically we call it the stress perturbation. So if you look at this stress perturbation over time for the upper cluster, which is here, so you can see that here the stress perturbations are quite large because of this proximity to the injection wells. So here is the values around 20 to 30%. But when you look at the lower cluster in the regions outside of the reservoir interval, we can see that actually the stress perturbation is much lower, is around 2%. And what it means in practice is that this lower cluster is actually very close to failure before any injection operation happened in the field. So what we think that is happening is that these earthquakes or this fault by itself was already very close to failure because of this orientation, so it's critically stressed. And therefore these earthquakes in the outside of the injection interval, they should be classified as triggered. Whereas the earthquakes in the near the injection well, they should be classified as induced because they were resultant from this massive amount of pore pressure that happened at the injection location. Okay, so what did we learn from this Rangaly experiment? So we revisit this classical experiment. So basically we learned that pore pressure diffusion along a damage zone was the main mechanism for seismic occurrence outside of the injection interval. So we think that the fault in its original state was already very close to failure. So what the experiment did was literally give the missing amount of energy to trigger earthquakes outside of the reservoir interval. And our results seem to support this idea that if the fault is well oriented in subsurface, then it's critically stressed, because depending on the orientation of this fault with respect to the maximum horizontal stress, then this fault only takes a small amount of energy to destabilize the fault and induce earthquakes. Okay, so we can now move on to a second case study where I will show the application of this coupled flow in geomechanics modeling. And now, instead of wastewater, we injecting CO2 in subsurface. So basically, there is a pilot CO2 storage case located in Illinois. It's the city of Decatur here in the United States. And the idea is that they injected 1 megaton of CO2 over the span of 3 years. So 1 megaton of CO2 is a very small amount of CO2, especially over the span of 3 years. It's not really a lot of CO2, but they recorded a significant amount of events. So this is between 2012 and 2015, 16. And then these events are actually small. So the magnitude -1 on average. So these are very small events. So these are micro earthquakes. But what is interesting about regarding this specific case is that when you look at the injection rate, which is shown in red, it really doesn't have a lot of temporal correlation with the seismicity rate, which is shown here in black. So we want to understand, okay, how and why did the CO2 injection in this case trigger the seismicity in this location? So when you look now at the seismicity in a map view, so this is a map view of the seismicity. So the injection takes place in this well called CCS1 well. The VW1 well is a monitoring well that they use to monitor the pore pressure variations in the reservoir. And you can see that the seismicity is aligned roughly according to this direction, which is the orientation of the maximum horizontal stress. And here we can see that the seismicity expands from the early and close to the well to later on, where the majority of the seismicity actually happens in this cluster number 4. So again, the question that we're trying to answer then is why and how did the injection of CO2 in this well trigger earthquakes in these areas? So note that this distance here is around 1 kilometer long. Okay, so when you look at a map view, on a cross-section view now, so we have the injection happening at the CCS1 well. So these are the sediments where they inject. So this is called Lower Mount Simon Formation. So this is the monitoring well, the VW1 well. And you can see that the seismicity tends to become deeper as it becomes further away from the CCS1 well, which is the one where the injection happens. So this is an important information because we're going to use it to actually map fault planes in this cluster of events in this area here. But let me tell you first a little bit about the structure of the reservoir so that you can understand a little bit about the pressure variations. So the CO2 injection takes place at the Lower Mount Simon, which is a very porous and very permeable sedimentary rock in this area. But one of the problems of this Lower Mount Simon is that it has lots of vertical or very thin mudstone buffers that actually compartmentalize the pressure vertically. And this actually is important because you can actually see that on observations of the reservoir pore pressure. And this is exactly what they measured. So as I mentioned, there is the CCS1 well, which is the injection well. And then there is a monitoring well called VW1, which is used to monitor the pore pressure variation in this location due to the CO2 injection. And when you look at this pressure variation over time that's collected at the VW1 well, we can see that the different colors are just different sensors. So the sensors go from the WB1, which is essentially in the basement, all the way to WB7, which is on the top of the Lower Mount Simon. So all this upper section here, this is sediments, and here is the basement where the seismicity happens. So you can see that there is a very different signature between this WB2 and 3, which is in the injection interval, and these other sensors, which is above the injection interval and below. For example, the WB1 is a much smoother variation than the other ones. So this is something that we need to take into account because it indicates that there is some vertical compartmentalization in the lower Mount Simon. And this is important because when you perform these flow simulations, you have to account for that as well. So one important aspect of this work is that we have interpret a lot of faults based on 3D surface seismic data. Okay, so these are the fault planes on the left. And also using the microseismicity locations, we also have interpret these faults that could potentially serve as locations for where this microseismicity is happening. So this is a map view here from the top of the basement. And you can see that actually the fault planes are located mostly like everywhere, but these are the ones that correspond that are exactly at the location of the microseismicity. Those were interpreted based on the microseismicity locations. Those are actually not possible to be seen using only the 3D seismic data. And I just want to give you a perspective view of the fault model. So this is the fault model, and these are the earthquakes. And then this is the basement surface. So this is just to indicate that the events are located mostly into the basement section. And as we did before for the rangelet, so the idea is that we need to build a computational mesh that adapts to all the faults and the horizons of our geological model. So basically, in this case of the indicator, so there's quite a lot of faults, so which makes the meshing process actually quite difficult, but still possible to be done. And here we're talking about roughly around 1 million elements, and they're very fine near the faults, and they course away towards the boundaries. Okay, so here now we want to perform flow simulations using two-phase flow. So we assume that the fluids are immiscible, so just an injection of CO2 into a brine formation. So this is the injection schedule. So this is around 1,000 tons of CO2 per day. And here we assume, so this is the compressibility of the brine into CO2. So basically the CO2 is much more compressible than the brine. And for the relative permeabilities, we went to the literature and we found these references that have reported some relative permeabilities for the CO2 and water for that area. So basically the idea here is that we want to describe how does the presence of one phase interferes on the flow of the other phase, in this case, brine and CO2. Okay, so let me talk a little bit about the boundary conditions and what is the state of these faults prior to any injection activity. So one way that we can quantify the proximity of a fault to failure is to look at the slip tendency, which basically tells us the ratio of the shear to effective normal stress. So the idea is that if the slip tendency is high, or the maximum value in theory should be around 0.6, 0.7, which is the typical values for friction coefficient of faults. So the idea is that the higher the slip tendency, more close to failure these faults should be. So for preferred initial stress model for this area, so basically we can see that these faults that are located in this cluster, which is called cluster 4, so these faults are actually very close to failure. So basically, the shear to effective normal stress is around 0.65, which means that these faults are critically stressed in ways. And what is interesting to see is that, so this is the orientation of the maximum horizontal stress. So you can see that some faults that are perpendicular to this maximum horizontal stress orientation, they have a very low or small slip tendency, which means that these faults are probably not going to be destabilized at all. So this serves as a basis for us to understand what is the state of these faults prior to any injection in this case. And we can use this information to predict that, even if some small amount of pore pressure changes, it can destabilize this region here because this area is actually very close to failure in its in situ state. Okay, so the question that we are chasing in this specific work is what is causing the microseismicity at the indicator, CCS site. So we want to understand in depth, like whether this microseismicity is caused by either pore pressure diffusion or by poroelastic stresses. So if it's caused by pore pressure diffusion, Then we want to understand which hydraulic mechanisms that control the destabilization of faults at this cluster 4, which is very far away from the injection well, CCS1. And here we have two hypotheses. One is that pore pressure could be diffusing through the low permeability basement, or pore pressure could be diffusing through fractures and faults that are in the basement, and the ones that I showed you before. And the second hypothesis is whether this destabilization could be happening actually due to poroelastic stresses. Okay, so we know that the changes in column failure function can be expanded to be separated by a term that is given by the poroelastic stress, and another term that we call it just the pore pressure effect. So this poroelastic stress, the idea is that it's just the difference of the shear stress at the fault plus the friction coefficient and the total difference in the normal stress at the fault. And this is totally independent of pore pressure diffusion. So we want to understand which of the two mechanisms is dominating the destabilization of these faults. Okay, so we can start with the hypothesis 2. So looking at the poroelastic stresses at cluster 2 and 4. So remind you that the cluster 2 is the one very close to the injection well, and cluster 4 is this one very further away. So here what I'm showing is this term that are called poroelastic stresses over time. And the histogram, this is the number of events at cluster 2. And the blue line is the poroelastic stress value. And you can see here, note that the values are all negative. And what this means in theory is that these are the stabilizing values. So meaning that the poroelastic stress changes are actually stabilizing the fault. And in the cluster number 4, which is further away from the CCS1 well, these changes are actually so small that you cannot really distinguish it from zero. It's on the order of kilopascals, so it's much smaller than the cluster 2. And the reason for that is because this cluster is just simply too further away from the CCS1 well. But the main conclusion, at least from this idea here, is that the poroelastic stresses due to the injection, they are negative or they're stabilizing. And the reason for that is because when we inject, similarly to the Rangaly case, you're causing this volumetric expansion of the reservoir that induce normal stress changes at the fault that compacts the fault or clamps the fault. So what this means is that pore pressure, similar to the Rangaly case, is also an important mechanism in this case. And now we can test this hypothesis by measuring the pore pressure over time for these two clusters. And here I'm showing two lines. So this is pore pressure over time, okay, for the cluster number 2, and here is cluster number 4. And the idea is that the red line is a pore pressure for a model that I don't have any faults, just diffusion through a very low permeability basement. And the blue line is a pore pressure diffusion through the basement plus faults, okay? So you can see that if you don't have any faults in the model, you can perhaps say that pore pressure destabilize these faults that are very close to the well. But in these faults that are very farther away from the well, from the injection well, the pore pressure changes are pretty much near zero. So we need faults to transmit this pore pressure, to allow pore pressure to diffuse from the injection well to the regions in cluster 4. Because in this case, we can see that the pore pressure increased to the order of maybe 0.5 to 1 megapascal due to this pressure diffusion along these faults. And what we can learn from this, or what you can see from these results, is that having these faults, including these faults in a coupled flow geomechanics model, and modeling pressure diffusion along these faults is essential to explain the destabilization of faults due to the CO2 injection, in this case, a CCS1 well, especially the faults that are very further away from the injection well. If you did not have any faults in the model, for example, there will be no way to explain this destabilization of cluster 4, for example. Okay, so I've been telling you that pore pressure diffusion along faults is important, and specifically in this case of the geological carbon sequestration is actually the mechanism that destabilizes faults further away. So I want to show you a 3D view and a movie that's going to show the pore pressure variation over time and in space as well in the faults. So basically you have the CCS1 injection well, and in blue those are all the fault planes, and the circles are the micro earthquakes that are located during this injection. So when I play this movie, let's see if it's going to work. So you can see, so these are pressure changes with respect to the initial time step. So basically, we can see that near the injection well, okay, so the pressure changes are quite large because these faults are very close to the well, so the pore pressures are larger. But as you go further away from the injection wells, there is also some pore pressure changes at these planes that are where the micro earthquakes are located. And you can see there's two differences in colors. One is the pore pressure changes are near zero, and the other ones are not. So this region on top is actually the fault segments that are located in the sedimentary section of the lower Mount Simon. And this region on the bottom that illuminates, so this area is the one that's the fault sections that are in the basement. So essentially, the permeability of these faults in the basement is so large that actually you have pore pressure changes throughout the whole faults in the basement. And one thing that is quite interesting here, if you notice on the left, this fault here is actually hydraulically isolated from the other ones. So it is not communicating, it's not intersecting the other faults. And you can see that the pore pressure change is actually zero in that fault, which reinforces this idea that if these faults are not communicating, not connected with each other, then there is no pressure communication in the basement section, because the basement has very low permeability. I just want to play again the movie so you can see the. So this is how the injection takes place at CCS1 well, and then as the pressure, as time advances, you increase the pore pressure in this region where the earthquakes are happening. And this pressure changes at this region only occurs due to this long fault pore pressure diffusion that we included in the coupled flow in geomechanics. Okay, so what we learned from this coupled flow in geomechanics modeling associated with CO2 storage indicators. So basically, we think that pore pressure diffusion through these basement faults is the main mechanism for fault destabilization due to CO2 injection. We think that poreless stresses are negative, and meaning that they're stabilizing, and much smaller than pore pressure. So especially away from the injection well, the poreless stresses are really negligible. And one key message of this work, and I think it goes along with the Rangaly work that I presented before, is that the ability to represent these faults in the coupled flow in geomechanics modeling is essential to predict fault destabilization. I think that having models that don't account for flow along faults is you probably would be missing a lot of key physics that are important to explain why earthquakes happen, not only close to injection wells, but also further away from the injection wells. And I would like to just, before concluding, I would like to just mention a little bit about some current work that are being performed now as a postdoc. So, okay, so we turn our attention now to the Los Angeles Basin, which is located in California. So Los Angeles Basin has a very long history of oil and gas production in the United States, especially. So basically, there's a number of oil fields. So this figure here is all these different contours. There are different oil fields that are located in Los Angeles. So this is downtown Los Angeles here. And these oil fields have been producing for a long time. And as you know, also California has a number of earthquakes that happen perhaps naturally, perhaps induced due to the anthropogenic activities. And here we have selected one oil field, which in this case the Wilmington, which is actually the largest oil field in this region. It's actually the fourth largest, I believe the fourth largest oil field in the United States. It has been producing since 1936 and is quite structurally complex. There's a number of faults, as you can see in these white planes. And the most important, there is a major thrust fault, which is this green plane, which is called the Wilmington fault, which is capable of generating earthquakes of magnitude up to 7. And this oil field has been producing since 1936, has hundreds of wells, and we want to understand what is the impact of this extensive oil and gas production, not only in this oil field, but in the basin in general, on the induced seismicity in this area. So basically, the questions are, does the induced seismicity, does the production helps or prevents induced seismicity in this area, or earthquakes in this case? So in summary, the conclusions that I have here is that I showed the two cases of injection-induced seismicity. One is the Rangaly, the associated wastewater case, and the Decatur associated with CO2 storage. And they both indicate that a long fault pore pressure diffusion is an important mechanism for the destabilization of persistent faults. And advanced computational models are required to honor realistic subsurface geological structures. So basically, we have to account for the geology that is in subsurface, especially because these faults are very often no planar. They're very complex. And coupled multiphase flow in geomechanics is a useful tool to explain the mechanisms that lead to fault destabilization associated with anthropogenic activities. And with that, I would like to thank again for the invitation and open up for questions.
Thank you, Josimar, for your presentation. Well, it's very interesting job you're doing.
Thanks.
Let's open for questions. You may write on the YouTube chat or talk here directly to him. So let me see if there's any question there.
Josimar, tem umas perguntas.
Ok, Marcelo, tudo bem?
Espero que você ainda entenda português, porque eu vou fazer as perguntas em português.
Não, claro.
Parabéns pelo trabalho.
Obrigado.
A primeira pergunta é a seguinte: esses modelos geomecânicos e de propriedades poroelásticas, um dos parâmetros principais é a permeabilidade nas falhas. A permeabilidade das falhas, isso é um parâmetro que você põe no modelo até ajustar os dados, ou você tem medidas independentes dessas permeabilidades?
É uma boa pergunta. Nesse caso, é muito difícil ter a medida independente da permeabilidade, porque requer que a gente tenha, talvez, como é que fala? Dados, né, que você tem. Vou responder em inglês, professor. So we need pressure data most of the time to be able to say something about the fault permeability. So most of the time, so in this modeling, I have to use a number, a fault permeability value that I think is reasonable for the fault. So it depends as well. So small faults that don't have a lot of slip, they tend to have, how can I say, especially in a crystalline basement, they have a larger permeability. So if they have in a crystalline basement, so if it's in a sedimentary section, then the permeability is low. But we don't have data to constrain the permeability directly of the faults. It's something that we need to input in the model. Não sei se respondeu essa pergunta.
Sim, respondeu. Outra pergunta é, nesse segundo caso aí de Illinois, quer dizer, foi uma coincidência que os sismos acabaram ocorrendo perto do poço de monitoramento e não perto do poço de injeção? Quer dizer, você esperaria que perto do poço onde você está injetando o gás carbono aí, é onde você teria mais chance de ter sismicidade, né? E a sismicidade foi ocorrer no poço que está lá só para monitorar as coisas.
Exato. Na verdade, se a gente olha na map view, a gente vê realmente que a sismicidade está longe do CCS1, que é um injetor. Eu acredito que não teve muita sismicidade aqui nessa área, porque talvez não tinha falhas mesmo que geraram a sismicidade, né? Então, e também tem a questão também da orientação dessas falhas, né? Porque se se as falhas não estão orientadas de uma maneira que facilite que o sismo ocorra, né? Então, realmente não vai acontecer. Então, aqui, por exemplo, né, uma das coisas que a gente fez aqui, usando esse sleep tendency, algumas falhas que estão perto do CCS1, eles têm um sleep tendency muito baixo. Outras têm um sleep tendency até um pouco alto, mas é interessante que não tem nenhum sismo aqui, né? Então, particularmente, eu não sei explicar por que o sismo não ocorreria nessas falhas aqui, né? Mas o que a gente percebe é que as falhas onde o sismo estão acontecendo, realmente elas têm um sleep tendency muito alto, né? O que parece que corrobora essa ideia, né, de que se a falha estiver orientada de uma maneira preferencial em relação ao máximo horizontal stress, então isso facilita muito, né, que o sismo ocorra.
E essa tendência, o sleep tendency aí, depende da orientação da falha, porque essas falhas aí não são todas verticais, né? Imagino que cada uma tem um mergulho diferente, porque eu esperaria que a parte das falhas que são paralelas ao SH máximo também deveria ter uma tendência baixa, né?
Exato, mas aqui as falhas são muito não planares, né? E se você olha na visão 3D, você vê que tem muita curvatura, tem muita não são planos realmente 2D planes, né?
Sim.
E isso aí foi os geólogos, né, que são colaboradores nesse projeto, eles que interpretaram essas falhas, né, usando sísmica 3D. E no caso, eu também fiquei surpreso com a quantidade de curvatura que eles incluíram nas falhas, mas pode ser que faça sentido, talvez, em geral, né, que essas falhas tenham bastante curvatura ou não, né? Então,
Muito bom, obrigado.
não, sem problema não.
Obrigado, Josimar. Bom, e acho que de certa forma, esses clusters de sismos aqui que está nessa imagem que você deixou, que não tão perto de falhas, poderia ser alguma falha não mapeada, por exemplo?
Não, com certeza. Na verdade, essas falhas que você está vendo perto dos eventos, nenhuma dessas falhas foram, na verdade, mapeadas usando sísmica 3D, porque simplesmente não tem resolução para ver, né, essas falhas.
Tá.
Então, o que a gente fez, só colocou uns planos verticais, não, subverticais, eles têm um pouco de dipping, que passam pelos clusters, e para tentar explicar, né, porque senão não teria como explicar por que o evento ocorreu aqui, né. E você vê que na verdade, tem bastante eventos que, por exemplo, esses eventos aqui,
Sim.
que não tem nada lá, não tem uma falha, não tem. Então isso quer dizer o quê? Que o nosso modelo de falhas ainda está precisando colocar mais faltas, né, mais falhas, mas é difícil mapear esses planos, né, porque a sísmica 3D ela tem uma resolução baixa e então é difícil, né? O maior problema, na verdade, desses projetos de sismicidade induzida é realmente você ter um modelo de falhas geológicas que te permita você ter confiança, né, que essas são as falhas que eu acredito que os sismos podem ocorrer, então, mas em geral são muitas falhas que a gente não consegue enxergar, né, com a sísmica 3D.
Tá ótimo. Obrigado, Josimar. Deixa eu ver se tem alguma.
A orientação dos clusters de sismicidade dá para mostrar se essas falhas inferidas são verticais ou não? Uma falha transcorrente vertical é mais difícil de ser detectada em sísmica 3D. Né?
É verdade, é verdade. E, na verdade, não tem uma visão 3D aqui dos sismos, mas uma visão 3D do sismo, você vê que, e aqui não tem os planos que foram interpretados baseados somente nos eventos, né? Então você vê que os eventos também têm certeza em relação à localização deles, né? Então, assim, a gente fez um esforço muito grande para tentar colocar planos que não fossem somente verticais, né? Porque tentar ver se achava algum pouco de dipping nesses eventos, mas, em geral, esses planos aqui que estão perto do CCS1, eles são bem verticais. Esse outro plano que está aqui nessa área, que corresponde com esses eventos aqui, eles têm um pouco de deep, né? Então tem um pouco de mergulho e então não é totalmente vertical, mas também são as falhas que são bem complexas, então eu imagino que o imaginamento sísmico dessa área aqui deve ser bem difícil, né? Acredito.
Obrigado, Josimar. Bom, no YouTube não tem mais questões. Eu não sei, Marcelo, você quer fazer mais alguma pergunta? Ou...
Não, acho que não. Acho que o trabalho é super interessante, esse aí, bem atual, né? Porque essa parte de sismicidade induzida por injeção e fraturamento hidráulico, isso é um assunto super importante, né? Então, muito bom.
Ok, obrigado.
Então, obrigado, então, Josimar. Parabéns pela apresentação.
Okay,
E obrigado
obrigado,
a todo mundo que assistiu.
Ok, obrigado pelo convite.